And it turned out to be, and it still is, extremely powerful tool. So if we're interested in the driving force for a particular reaction, we can quantitate that. But it's not solely based on energy. Typically when we think of thermodynamics, the two driving forces in nature. One is to minimize the energy. But what was the other driving force? Entropy. And what we want to do is we want to maximize entropy, which entropy is a measure of what? Disorder. And so that tells us what is spontaneous. Spontaneous just means it naturally occurs. Like a ball rolling downhill is spontaneous, but a ball rolling uphill, from a standstill start is not spontaneous. You don't expect things to fall uphill. We expect things to fall downhill. And so that's what we're looking at. But in chemical reactions, some of the chemical reactions can actually roll uphill by themselves, because of entropy. When you take physics, normally with physics, entropy is not a big issue because you're just looking at like one object. And the entropy of one object is not so significant. But in chemistry, when you encounter a sample, let's say a gram of sample just has such a huge number of atoms, it would be very difficult to count the number of atoms in a gram of anything, because the number would be so enormous. And so when we're dealing with a whole bunch of particles, then entropy becomes a significant factor, and we have to worry about that. And so normally when we think about gravity, everything goes downhill, nothing goes uphill, nothing falls to the ceiling. But when I think about chemistry, then we have to shift that thinking a bit because. And so the first thing is let's go back to energy and look at energy. We had the total energy, and then we had U, the internal energy, and H, the enthalpy. And so what's the difference between these three here? What do we primarily look at?
Total energy, E is kinetic energy plus potential energy.
Yeah, it's the kinetic energy plus the potential energy. Normally, in physics, it's like gravitational. This is gravitational potential energy. It's not moving, but it has gravitational potential energy because it could fall down. That gravitational potential energy can be converted into kinetic energy, the motion of it falling down if I just let it go. Right? Then that is converted into kinetic energy and it hits. Well, the same thing in chemistry. We have chemical potential energy and kinetic energy. And I've already talked a bit about that before. And so it's a different type of potential energy. We don't really care too much about gravitational potential energy, but we do care about the chemical potential energy. And the chemical potential energy does it have potential to react? Like a very reactive mixture would have high chemical potential energy versus a very stable mixture, which would have low chemical potential energy. And so whenever we're looking at it, well, it's the same thing here. The internal energy in E is basically the same thing. We're looking at kinetic energy and potential energy. Internal energy is the total energy. The situation here is this. When we're looking at energy, we have to define things because the first law of thermodynamics is. Does anybody recall what the first law of thermodynamics is? The first law of thermodynamics, everybody learns, I think, Chem 4, and that is energy can neither be created nor destroyed. Basically, that's the first law of thermodynamics. And so what that means is if energy is neither created nor destroyed, that means the energy content of the universe is fixed. And so there's, you can't have more energy, you can't have less energy, right? Because the energy can neither be created nor destroyed, but so the total energy of the universe is fixed. In that sense. So what we have to do in order to use the first law is we have to define, because if something loses energy, how could it lose energy? Because energy is not destroyed, so how is it being lost? Well, the heat or what is it?
It's just leaving the system.
Yeah, leaving the system. So whenever we deal with the first law, we need to know, that the universe consists of the system and the what? Surrounding. There are two types of systems that we look at. One type of system is just an object, a physical object, a piece of metal, a hot piece of metal. If you have a hot piece of metal, it's going to cool down. And that would be a system which is an object. And so a system consists of, one, an object, a physical object. It could be a cup of water, a hot piece of iron. And what can happen is that the hot piece of iron, or could be dropped into the cold water. And so those are the two objects that we can look at. And then what we'll have to do is we'll have to define those, because the surroundings will be the same thing. And so the other type of system is like a process or a reaction. A process, I call, like, the process would be like melting, or boiling or freezing, etc. That would be a process. And so, let's say the hot piece of iron melts. Okay, or a reaction would just be a chemical reaction. The surroundings will be the rest of the universe. So let's take a look at an example here. An example would be this. Let's take methane gas and 2 oxygen gas. And this is going to be at 298 Kelvin and 1 atmosphere. Now, there are different ways of visualizing a mixture like this. And so this is a little bit of a review of the gas chapter. I think it's chapter 6. But if I have 1 atmosphere total pressure, and then I have a 1 to 2 mixture here, there are 2 ways of describing this mixture. One way of describing this mixture is via Dalton's law. Normally when people think about a gas mixture, they think of Dalton's law. And so if you think about Dalton's law, then what would the pressure of the methane be in this mixture?
1 atmosphere.
1/3 of an atmosphere. And what would the pressure of the oxygen be? 2/3. 1/3 plus 2/3 gives us 1 atmosphere. That's Dalton's law. In thermodynamics, sometimes we use Dalton's law, but most of the time when we think about a mixture, we think in terms of Avogadro's law. In Avogadro's law, how many atmospheres of methane do we have? In Avogadro's law, we have 1 atmosphere of methane. How many atmospheres of oxygen do we have? 2? 2? No, not 2. It's not 2. How many atmospheres? 1. So we'd have 1 atmosphere of methane and 1 atmosphere of oxygen. Well, how could that be? Dalton's would be 1/3 and 2/3, right? but we visualize the mixture differently. In terms of Avogadro's, the difference is this. In Dalton's law, let's say I have this and I have a certain number of liters. In Dalton's law, the volume of the methane is equal to the volume of the oxygen. In Avogadro's law, no, it's not. We'd have twice the volume of oxygen as we have methane. So let's say I had 1 liter of methane, I'd have to have 2 liters of oxygen, all at the same pressure. And so, in other words, the key difference between Dalton's and Avogadro's is Dalton's law, we do things under constant volume conditions, and the pressures can change under constant volume. We call that bomb calorimetry or whatever. We got to do it in the bomb because if the pressures become big, then it could explode if the volume containment is not strong enough. And so typically in Dalton's, we do this in a bomb because we need to maintain constant volume. However, if we do this under Avogadro's, that's what we call constant pressure. So constant pressure is like a balloon, So if I have 1 liter here, then I need to add 2 liters of oxygen. That's going to give me 3 liters of total volume. Otherwise, the pressure is going to change. Does that make sense? Here. And so there are 2 ways to do this reaction here. We could do this under constant pressure, or we can do it under constant volume. 2 ways. Constant pressure or constant volume. What do you think most people do in the laboratory? Do they do their reactions in the open lab and just let the pressures equalize, or do they do it in a bomb? In a bomb? Yeah, you would think so, but it's just kind of a hassle to do it in a bomb. It's much easier. Like say, for example, if I burn methane here, I'm not going to do it in a bomb. I'm just going to do it in the open lab. And so what that means is all the pressures are going to be equalized. That is, the pressure of the oxygen has to equal the pressure of the methane, which has to equal the pressure of the CO2, which equals the pressure of H2O gas when it forms initially, which equals the pressure of the room. Otherwise, if you have a huge pressure, there's going to be slight overpressure here. Slight overpressure would be it's like a half psi. Actually, that's what the pressure of the natural gas is 1/2 psi over room pressure. So that's what brings up a key difference between this, because what H is equal to is H is equal to the internal energy or the total energy plus PV, pressure volume. Pressure times volume is equal to energy. Okay, so let's go back to this for right now. I'm talking about this. Here, go back to this. How much energy we get from this reaction depends on how we do it. So, for example, if we do this under constant volume versus constant pressure, do you know we get a different amount of energy? Do you know what gives us more energy if we do this reaction under constant pressure or under constant volume? So if we did this in a bomb, we'd get a different amount of kilojoules per mole of reaction, per mole of methane, than if we did this in the open lab. Do you know which one gives us more energy? Constant pressure. Yeah, it turns out constant pressure does, but it depends on the reaction. In this reaction, the reason why constant pressure gives us more energy is, well, what forms from this reaction here? When you take methane and burn it, it forms what? Carbon dioxide and water. Is carbon dioxide and water at a higher chemical potential or a lower chemical potential? It's at lower. So we know that CO2 gas and H2O liquid. We're going to go to liquid. Why are we going to go to liquid? We're going to go to liquid. It's because of this. What we're going to do is when this first burns, the H2O is going to be hot. It's going to be steam. It's going to be gaseous. But what we want to do is whenever we have a reaction or process, what we want to change is we want to change the potential energy. We don't want to change the kinetic energy. So what I'm going to do here is I'm going to let this reaction cool back down to 298. When the reaction mixture cools back down to 298 Kelvin, then the water is going to come out as a liquid because liquid water is more stable at 298, and it's going to be at 1 atmosphere. Okay, so what I've done here is I've kept the kinetic energy the same because kinetic energy only depends on temperature. That's from kinetic molecular theory, way back when. And I'm only going to change the potential energy here. And so what we can say is this. We can say that U initial and U final, let's take a look here. So we'll have U initial and U final. Okay, one of the things that we can do for this is we can just say that U initial is equal to the kinetic energy initial plus the potential energy initial. And then U final is equal to the kinetic energy final plus the potential energy final. And so in other words, what we're going to have is we're going to have a delta U. Delta U is going to equal delta, the change in the kinetic energy, plus delta, the change in the potential energy, delta PE and delta EK. Was there any change in the kinetic energy? No, there's no change in the kinetic energy. So the change in the kinetic energy is 0. And so that means the change in internal energy is just the total change in potential energy here. All right, this is the system. And so what I have to do is I'm going to put U down here in the system. And the system is not an object. The system is a reaction. And this reaction is going to produce energy. And this energy is going to be equal to the change in the potential energy. But the odd thing is, at the end of this reaction, do we have any methane and oxygen left? No. So that disappears. But we're left with CO2 and water. The residual CO2 and water, this is a product of this reaction. Would that be the system? So the system converted from a reaction to the products, object. And it turns out, no. This is weird, maybe not. But what happens is the system is the reaction, and whatever's left over will be the surroundings. So the CO2 and the water that's left over here, now that's part of the surroundings. So the reaction occurs, and then this is going to be exothermic. It's exothermic because we lose energy. We're going from higher energy to lower energy. Where does that energy go? Well, the first law of thermodynamics says that energy can be neither created nor destroyed, so that energy has to go somewhere. Where does the energy go? Into the surroundings. And so our delta U of the system, whatever the system loses or gains, that has to come from or go to the surroundings. And so delta U of the system is equal to minus delta U of the surroundings. Usually in Chem 1A, we're dealing with heat. You know, hot object cools down. A hot object cools down, it's got a lot of kinetic energy, you know, and so if I have an object, let's say, we've seen this, like a hot piece of iron. And so this might be, let's say, 50.0 grams of iron solid at 200 degrees C. And then, well, that's a high temperature. And then we're going to go down here, we're going to let it cool back down to room temperature. Room temperature, this will be 50.0 grams of iron at 25 degrees C. So here we have a delta U. Delta U is going to equal the delta, the change in the kinetic energy, plus the change in the potential energy. So when we look at this, the change in kinetic energies is related to the temperature. So here we have high temperature, it's got a lot of kinetic energy. Here we have low temperature. And then heat's going to be exchanged because some of that kinetic energy is going to be given to the surroundings as heat. And so here, delta EK is going to be a drop in the energy, so we're going to lose energy. But what about the potential energy? Did the potential energy change at all in this? It turns out if I have 50 grams of iron here and 50 grams of iron here, is there any difference in the potential, chemical potential of that for reactions? No. And so delta PE is equal to 0 here. So what we try to do is we try to not mix things up. If we have a reaction or process, we need to make sure we start at one temperature and end at the same temperature. The only reason for that, we don't have to do that. The only reason to do that is to keep the math simpler, because then we only are dealing with one equation rather than two equations. We'd have to factor in the potential energy and we have to factor in the kinetic energy. It's not hard, but you know, it just keeps adding more and more equations to it. And so to keep things simple, whenever we have a reaction or process, the change is solely going to be in terms of potential energy. We've got to make sure we start at the same temperature and stop at the same temperature. If we don't, then we have to factor in kinetic energy. Factoring kinetic energy is not difficult, but we have to figure out, you know, Q is equal to, you know, when we factor in kinetic energy, we usually use the MC delta T. Delta T giving us an indication what the change in kinetic energy is. So Q is equal to MC delta T. We'd have to do an MC delta T calculation for all these objects that are left over here. Here, here we don't have to factor in potential energy. There's no change in potential energy, so this is a simpler case. And in the simpler case here, we have, you know, Q of the system is equal to minus Q of the surroundings. And do you recall what Q is here? Q is heat. Heat is the transfer of kinetic energy from higher kinetic energy to lower kinetic energy. So basically, you're going to have hot iron atoms moving very rapidly, and this is going to probably transfer to the air surrounding. The air is going to get hot. You know, in other words, some of that motion from the collisions will be imparted to the air. The air gets hot. That means the surroundings will get hot. You know, as the object cools down. So there are two ways of doing this reaction process. One is under constant volume. If we do things under constant volume, we use U here. Use U. If we do things under constant pressure, we use H. Now, why do we use H under constant pressure? The reason why we use H is this. I forgot I was going to do a little demo, but I have to grab the balloon. If let's say if you blow up a balloon, does that require work? Yeah, it's not so easy to blow up a balloon, and the bigger the balloon is, the more work. Also, the bigger the external pressure. Let's say you tried to blow up a balloon underwater. If you tried to blow up a balloon like 9 feet underwater, is it going to be more difficult or easier? It's going to be more difficult because you got to fight all the water pressure. The water pressure is going to be huge at 9 feet. It's going to be difficult to blow up the balloon. And so to blow up the balloon requires work. But, if we have a reaction that's under constant pressure, then if more gas is formed during the reaction, that's like blowing up the balloon. And that means you're going to have to fight against the surroundings, whatever the surroundings is. If the surroundings are just, let's say, normal sea level, 1 atmosphere, then it's going to require maybe less work than it is to blow it up underwater. And blowing it up underwater and blowing it up at sea level would require more work than blowing it up out in space, let's say, where there's not much you have to fight against. So it depends on what the surroundings are. The surroundings are going to dictate how much work you have to do in blowing up the balloon, right? How about deflating the balloon? Let's say you want to deflate a balloon. You deflate a balloon, like let's say you blow it up and you're pinching it closed, and you bring it underwater. It's going to deflate pretty rapidly because the high pressure is just going to squeeze the air out of it, right? Versus deflating it at sea level in air, it's going to deflate a little slower. Versus if you bring it out in space, how fast will it deflate out in space? It might not really, Well, it depends on where you blow it up. If you blow it up at sea level, if you blow it up at space, out in space, it might not deflate so fast. And so that also, how it deflates depends on what's squeezing it, the balloon, and so that's the surroundings. What's squeezing it is the surroundings. And so here, what I look at this, I'm looking at this. Do you know the molar volume of the gas? You guys have to memorize that? I had to memorize that in like Chem 4. I had to memorize it. 22.4 liters per mole at STP, right? 22.4 liters per mole. I memorized it. I spent time memorizing it, but I never used it. I never used it, and I still really haven't used it, although our Chem 4 book has lots of questions of molar volume at STP. What I found to be much more useful is to memorize the molar volume of the gas at room temperature and 1 atmosphere pressure. Do you know the molar volume of gas at 1 atmosphere and room temperature? It's an easy calculation if you ever forget. The molar volume of a gas is the volume per mole. The volume per mole, PV equals nRT, so this is RT over P. And so the most useful molar volume for me is when we have, R, I'm going to do in atmosphere, 0.08206 liters times atmosphere per mole Kelvin. So I have 4 sig figs here. And then temperature, we can do 298.15 Kelvin, so that's 5 sig figs. And the pressure we're just going to do is exactly 1 atmosphere. So we should be able to get this for 4 sig figs. So let's figure out the molar volume for 4 sig figs. We can do this in the bar too. I probably should do it in the bar as well. 0.08206 times 298.15 divided by 1. 24.466. liters per mole. So 24.47 liters per mole. Or, or roughly, this is 24.47 liters per mole, or roughly 24 and a half, depending on how precise you want to be, liters per mole, or about 25 liters per mole, if you don't need to be very precise. So at STP, standard temperature is 273 Kelvin, and so if we warm it up, we're going to get more volume, and so at room temperature, it's going to be a little bit bigger as far as the space it occupies. How about if we're at 1 bar? What's the molar volume at 1 bar? So this is at 298 Kelvin, room temperature we call that, and 1 atmosphere. So if I have a bar instead, I'll convert atmospheres to bar. So let's go up this way. And so do you know the conversion? The bar is a little bit smaller than an atmosphere. So there's 1.01325 bar per atmosphere. And so let's go, since the bar is a little bit smaller, pressure, then the volume is going to be a little bit bigger because it's not being squeezed as much. So I'll take this number that I just had in my I still have it in my calculator, times 1.01325, 24.790. Equals 24.790 liters per mole, or the 4 sig figs, 24.79 liters per mole, or about 25 liters per mole, roughly. If we don't need to be so precise, and for this, we're not going to be very precise. So this is Avogadro's. Avogadro says, okay, 1 mole of methane occupies what volume at? Not at STP. If I said 1 mole of methane occupies what volume at STP, you'd say 22.4, right? But how often do you burn methane at 0 degrees C? Well, I guess if it's that cold, you want to burn methane because you're probably freezing cold. You want to keep warm, so you're probably burning methane at 0 degrees C. But most of the time, we don't work in a laboratory that's at 0 degrees C. I visited a place where they work at below 0 degrees C. I visited a place where they worked at -5 degrees C. It was in, what was it? Somewhere east, downtown, LA, in this warehouse. Everybody was dressed like they were in Alaska. It was still hot outside. It was over 100 degrees outside. People would pop out. But all day long, they're dressed like they're in Alaska. And then I was thinking, oh yeah, they're probably working at STP, standard temperature and pressure. But it's unusual, And so this is much more. And so 1 mole of methane at 298 Kelvin and 1 atmosphere occupies what volume? Roughly. You don't have to be so precise. Just give me a rough. 25. 25 liters. 2 moles of oxygen occupies what volume? 50 liters. So altogether, how many liters do I have up here? I have 75 liters of volume. Okay, 1 mole of CO2 occupies about 25, and 2 moles of liquid water. 2 moles of liquid water, 18 grams per mole is 36 grams. 36 grams of water occupies what volume? 36 grams of water, that's 2 moles of water, liquid. It's a gram per milliliter, right? And so it occupies 36 milliliters or 0.036 liters. So this would be 25.036 or 25.04 liters, let's say. This would be 75 liters. So do you see what's happening here? We're going from 75 liters to 25 liters. And what's happening is the balloon is being deflated. The balloon's being deflated. Well, that's good for the system, because the system volume is being deflated. It's fine because the system doesn't have to do anything. But it's not so great for the surroundings because you know what? If the system's volume deflated by 50 liters, that means the surroundings volume must have increased by 50 liters. If the surroundings volume increased by 50 liters, then the surroundings had to blow up the balloon. And so this is a case where you can't get something for nothing, And so yes, if our volume deflated by 50 liters and the surroundings volume increased by 50 liters, that's work. So what we call that's work done by the surroundings on the system. And what that equals is this. This is why we get more energy if we do this under constant pressure. If we do this under constant pressure, the volume deflates by 50 liters, the surroundings did that work, and the system benefits from that. And so we actually get more heat. Let's say I'm trying to heat up a pot of water. I'm going to get more heat by burning this under constant pressure than if I did this in a bomb. If I did this in a bomb, then the volume cannot change. And if I do this in a bomb, the volume initial and the volume final is the same, so nobody blows up any balloon or anything. Nobody does any work that way. And so we're left with that. So let me add some more to this. When we look at the delta U here, and the energy that's exchanged between the system and the surroundings, let's say there's some heat generated, and it gets hot. And so the delta U is going to equal Q, whatever heat, actually, let me do this, there. So delta U is equal to Q plus W. This is delta U, the system, which is going to equal Q, the system, and work of the system. So whatever heat is lost or gained by the system, in this case, energy is lost. But the energy is going to either be given off as heat, which is what we want if we're heating up a pot of water, but we can also use this to do work. There are different types of work that we can do with this particular reaction. So, for example, there's some methane, like natural gas vehicles, compressed natural gas vehicles, CNG vehicles driving around. And this uses methane to drive the engine and do work that way. Or we can generate electrical. There are methane, what we call fuel cell, where the reaction is converted into electrical work. And so Q the system and W the system, well, this is going to equal, minus delta U, the surroundings, the change in the internal energy of the surroundings, which is going to equal, in this case, minus Q the surrounding, plus a minus W of the surroundings. Then we have a sign convention. Okay, the sign convention is this. If I have, the first law is often termed like this: Q of the system is equal to minus Q of the surroundings. That's another way of saying the first law. Whatever heat is lost by the system or gained by the system, will have to go to the surroundings, and so, or come from the surroundings. And so, what this sign means is this means the opposite. This does not mean exothermic. That just means the opposite sign of whatever the system is. So if the system's negative, then the surroundings has to be positive. If the system's positive, then the surroundings has to be negative. So it's the opposite sign. Okay, then we have this one. Q less than 0, that means lost heat, lost energy. Q greater than 0, that means we gained. And the same thing with work. Okay, if work is less than 0, we lost energy in doing work. If work is greater than 0, then we gained energy doing that work. And so we pay attention to the sign in our calculations most of the time. Sometimes we ignore the sign and just say it verbally. All right, so what we're going to get over here is this. The most common form of work done in chemical reactions. This is this is unavoidable at constant pressure. Is P delta V work. P delta V work is equal to minus P external times delta V. So what this is this is the work of blowing up a balloon. The larger the volume, the more work. The higher the external pressure, the more work you have to do. And so let's take a look. Let's say we blew up a 10-liter balloon. And so it would be quite a big balloon. But let's say that example here, delta V is equal to 10 liters, and P external, we're blowing it up under normal atmospheric pressure, 1 atmosphere. How much work was done? So we could calculate the work. The work would be minus P external. Well, P external is 1 atmosphere. And then delta V, well, we blew it up like 10 liters. And so the amount of work we did was minus 10 liter times atmosphere. Minus 10 liters atmospheres of work. That's how much work was done. Well, what is a liter atmosphere of work? And so let's take a look at this. Here. How many joules of work is this? Because normally in chemistry we think in terms of joules. Joules of work, or kilojoules. Actually, this isn't going to be joules, but how many joules of work is that? And so here, there's a conversion factor for liters atmosphere and joules. The conversion factor is this. We take R in joules per mole Kelvin, and divide that by R in liters atmosphere per mole Kelvin. Do you know what R is in the units of joules per mole Kelvin? A lot of people have it memorized. It's 8.3145 joules per mole Kelvin. That's our R. And then everybody has this one memorized, but most people have it memorized with 3 sig figs. We probably should have it to 4 sig figs. Liters atmosphere per mole Kelvin. And so if we take those two and divide them, what are we going to get? So let's go ahead and do that. Take 8.3145 divided by 0.08206. 8.3145 divided by 0.08206. And we're allowed 4 sig figs, so 1 of 1.322. And the units here will be joules per liter atmosphere. The mole Kelvin will cancel each other out. And so to 4 sig figs, 1 of 1.3 joules per liter atmosphere. That's our conversion factor. And so we can relate how many joules this will take. And so we just got to do 10 times that. Well, 10 times that would be 1,013. And so this would be minus 1013 joules or 1 kilojoule. We'll just say 1 kilojoule. And so that's going to cost us 1 kilojoule. It's minus because we're going to have to do the work and we're going to lose 1 kilojoule's worth of energy blowing up this balloon by 10 liters. Does that make sense? So, in this case, going back to this reaction, now, this is all over the place, but delta U of the system is equal to, the change in kinetic energy plus the change in potential energy. Delta U of the system is just equal to the change in potential energy, which is going to equal the work of the system the heat of the system plus the work of the system. So whatever energy was lost in this combustion reaction, the total internal energy is going to be converted into Q of the system plus W of the system here. And so what is that? Well, we can calculate the work of the system because the work of the system is just equal to, let me erase this here. Work of the system is going to equal, well, what happened? What happened was it's going to be minus P external delta V. So in this case, P external, that's just 1 atmosphere. And what is delta V? Delta V is V final minus V initial. And we're not doing this super precise. So V final is going to be 25, V initial is 75. And so this is going to be 25 liters minus 75 liters. 25 minus 75 liters. So that's going to give us minus 50. A minus times a minus is going to give us plus 50. 50 liters times atmospheres. And so what is that? Well, that's going to be 50 times 1 of 1.3. So 50 times 1 of 1.3, let's go ahead and calculate that. 5,065 joules, or 5.065 kilojoules. That's what it's going to be. plus. So plus means this. Plus means that the system gained energy from the surroundings and not lost energy. So it's kind of weird. To think about, but if we burn this in a bomb, we get 5 kilojoules less energy than if we burn this under constant pressure. If we burn this under constant pressure, we're going to get 5 kilojoules more energy. And so this boils down to what is H? H is the total energy of the system plus what we call the pressure volume state. The pressure volume state here allows us to figure out how that's going to interact with the surroundings. That is, are we going to get energy from the surroundings or are we going to lose energy to the surroundings? And so enthalpy here, and this is unavoidable if we do this under constant pressure. Under constant pressure, we need to know what this is. And so in other words, if we look at an enthalpy change, delta H is equal to delta U, the total energy of the system changing, plus how it interacts, how the system interacts with the surroundings. How the system interacts with the surroundings is either it's going to increase in volume, decrease in volume, or stay the same volume. If it stays the same volume, then there's no difference between internal energy change and enthalpy change. And so this is the most useful for us. Enthalpy and delta H are the most useful for us because we do most chemical reactions under conditions of constant pressure. It's very rare that we work with a bomb. And so what we want to know is we want to know what that PV state is or the P delta V state is. And so there's one more way of looking at this, and this is, the one more way of looking at this is like this. Think of delta H as your net income, your take-home pay, let's say. And then this is your, delta U would be like your gross income. P delta V would be like a tax or bonus, or if you live in a tax-free place, then there would be or no tax. You know? And so if you do this reaction in a tax-free place, that's like doing it in a bomb. You know, you do it in a bomb, there's no work that's going to be done by anybody, and therefore P delta V is 0 because a bomb you can't change, and therefore delta H and delta U are the same thing. But let's say you live in a high tax, state or whatever, then that means you're going to get a lot less energy than you gross. So your take-home pay is going to be a lot less. Or if you have a bonus, like in this situation, we have a little bonus. We're getting a little bit of money back. Maybe it's the gasoline thing, $200 or whatever. We get that, it's a little bonus that we can use. And this is the same thing. This is a little bonus that we can use. And so what I call delta H, the delta H is just the total energy, and then whatever P delta V work we have to deal with when we deal with it under constant pressure. And so H has a restriction. H is restricted. U is not restricted. H is restricted. What are the restrictions on H? You can only use H if what?
Constant pressure.
Yes. You can only use H, 1, if there's constant pressure, and 2, if there's PV work only. There could be other types of work, PV work only. what we can do is this. We can convert some of like the heat that might be generated because delta U is Q plus W, so we can get W. If there's no other work except this one, then that's what we consider here. But anyway, we'll look at this more as we go along. So this is always very confusing for people, so it takes some time to figure it out. So E, which is equal to U, which is not necessarily equal to H. Sometimes it's equal to H, U and H are the same thing if for example, there's no natural change in volume. But all these are energy, and we try to minimize energy. And then for reactions, we try to maximize entropy. And so how do we deal with entropy? Well, entropy is given a different symbol, S. And what we want delta S, to be greater than 0. If delta S is greater than 0, that is, the change in entropy is going up, then this is good. And this would be favorable. And, just like these, like delta H less than 0, it's exothermic. Delta U less than 0, that's good. And so this is what we want. If we have the energy go up and the entropy go down, then it's unfavorable. So this is favorable, and this is favorable. Okay, how do we calculate? We can get there are different ways we can get delta H. What are all the ways we can get delta H? All the ways we get delta H are, one, calorimetry, but calorimetry is kind of a hassle, coffee cup calorimetry. If we do bomb calorimetry, we get delta U, but we can convert delta U into delta H if we calculate how much work would have been done under constant pressure conditions. So coffee cup calorimetry works. No, bomb calorimetry would give us delta U, which can be converted into delta H. By just doing a work calculation, like pretending the reaction happened under constant pressure outside the bomb, how much work would have been done. If we did this in a bomb, no work would have been done. If we did this outside a bomb, then we would have had 50 liters volume change. And we just calculated how much work. So, and then we saw the difference, 5 kilojoules difference between doing it in a bomb and doing it outside. And so we can easily compensate for that. But calorimetry is a lot of work. It's much easier to calculate this. And there are many ways of calculating it, right? Hess's law, delta H's formation. You guys remember those? Probably the most common is delta H formation and Hess's law. That is, delta H of the reaction is equal to delta H of formation of the products. You sum all those up, minus the sum of the delta H's of formation of the reactant, etc. But how do we calculate delta S? So we can figure out what the energy change is. We've got to figure out what the entropy change is. And so the first thing is how do we measure entropy? And so this is a bit different. You know, when we do a delta H, do we ever do it this way? So for example, in all these calculations, do we ever do a calculation where delta H is equal to H final minus H initial? Do you ever do that? No, because we never have absolute enthalpies. The problem with absolute enthalpies is what is zero? What is the 0 point of energy? Or the 0 point of, so what we do is we just pick an arbitrary. So we never do this. Here. However, for delta S, we do. For delta S, all we do is we take the entropy final minus entropy initial. This is the way we calculate entropy. We figure out what the entropy of the products are minus what the entropy of the reactants are. And so that's a big difference. And the same thing with delta U. Delta U is never determined by taking U final minus U initial because the reason we could, but there's too much error associated with the determination of internal energy. And so we don't do it that way. And so how do we determine what the entropies are? Well, that brings us to the third law of thermodynamics. I skipped the second law of thermodynamics, but let's talk about the third law of thermodynamics first. First law says energy is neither created nor destroyed. Third law is this. Third law of thermodynamics states that the entropy of a perfect crystal perfect crystal means there's no defects, vacancies, that type of stuff, impurities. Entropy of a perfect crystal at 0 Kelvin is 0. And so this is one way of thinking about this is the Boltzmann view of entropy. Boltzmann's view of entropy deals with something called microstates. And this is the number of ways that you can arrange things. If there's only one way to arrange things, then it's going to have very low entropy, in fact, 0 entropy. There's only one way to arrange a perfect crystal at 0 Kelvin. What happens if you heat it up? If you heat it up, then the atoms start to vibrate. And as the atoms start to vibrate, then there are multiple positions that that atom can be in. And so that means there are many ways, that is many different ways we can arrange the atoms in the crystal, although they're all stuck in their lattice position, but they're vibrating. So the more ways we can arrange things, then the higher the entropy is going to be, because the more mixed up things can get, basically. And so we could do calculations with the microstates. The math here goes through, we can go through this math, which we aren't really going to go through this math much, but we're going to come up with the Boltzmann equation. This is the Boltzmann over here. And this is a Boltzmann equation. That is, the absolute entropy can be determined. Unlike the absolute internal energies, absolute internal energies and absolute energies can only be estimated. The reason they can only be estimated is because what is really 0 energy? If you have a hydrogen atom at 0 energy, what is that? Is that 0 Kelvin? No, at 0 Kelvin, there's still electron being held there, that kind of thing. So it gets complicated. And so here with this, this is Kb is the Boltzmann constant, Ln's the natural log, W is the number of ways. If there's only one way of arranging it, then the natural log of 1 is 0, and the entropy, the absolute entropy, is 0. And so what this is is you figure out how many ways the system can be arranged, you plug it in here, and then you can calculate the absolute entropy of this. But if we have an Avogadro's numbers worth of atoms, and then there are lots of different ways, the number is going to be huge here, but that actual entropy is not going to be so huge. Absolute entropies are around joules per mole, not even kilojoules per mole, but joules per mole, Kelvin. And so here they go through some more calculations. More calculations. And so here, let's take a look at this. The Boltzmann equation, equation 13.1, is deceptively simple. It suggests that S can be calculated simply by enumerating the possible microstates being the number of ways. As demonstrated earlier, the enumeration of microstates is straightforward when the system contains only 5 particles. So they did 5 particles, then you can figure it out. For a system containing a mole of particles, the number of microstates defies comprehension. And so if we had a mole of particles, this number is not only incomprehensible, but also uncountable. Fortunately, we don't have to count the microstates. We must simply accept that for a given system, a very large number of microstates is possible. In fact, we aren't going to use this. We aren't actually going to sit there, although people do sit there and figure out how many ways. This is statistical thermodynamics. We aren't going to do that. What we're going to do is this. We're going to determine what the absolute entropy is, how much entropy we have by experiment. And so let's take a look here, how we can determine that. Okay, this is still doing this. This is statistical thermodynamics. They're figuring out how many ways, how many microstates we can have. And so this would be like a theoretical approach to this. What we're going to do is an experimental approach to this. And so this is still counting the number of ways. This is a homework problem dealing with that. So there are 2 ways we can determine entropy, the absolute entropy. One way is use the Boltzmann, S is equal to K sub B, the Boltzmann constant, times the natural log of the number of microstates, number of ways we can arrange the system. 2, what we can do is, it turns out that the number of ways we can arrange the system is related to the heat. So for example, do you know water, does it have a high heat capacity or low heat capacity? Water has a high heat capacity. Compared to, let's say, metals would have a low heat capacity. And that means, what does that mean? Well, that means that when you try to heat up water, there are lots of ways water can absorb that heat. Because water, the water molecules can increase kinetic energy. Right? When they can increase kinetic energy, there's translational kinetic energy. What else? Rotational kinetic energy and vibrational kinetic energy. If you heat up a piece of copper metal, is there any translational kinetic energy? No, because it's solid. Is there any rotational? No, there's only vibrational. And so what we can do is we can get an idea that the number of ways that things can be arranged is related to the heat capacity. The higher the heat capacity, the more microstates, the more ways we can arrange things, and the higher the entropy. And so the other way of doing this is by heat capacity measurements. And so basically there's just this, that the entropy is related to the heat capacity, which we call Cp over T, basically. And what we're going to do is, in order to get the entropy, we're going to do some, this is kind of simplified version here. But we're going to do something in calculus called an integral. Integral is basically getting the area under the curve. Over from 0, this is over temperature range, from 0 to T. And what that's going to do is basically it's going to be, well, we know the entropy, because of the third law, the entropy at 0 Kelvin should be 0. So basically we're going to get this. We're going to get some heat capacity curve like this. So let's say water. You know, water's heat capacity, liquid water is down here, 4.18. And then there's a jump. Actually, this is solid. Solid water is like around 2. Then liquid water is about 4. And then gaseous water is around 2. Or steam. Or something like that. And then in order to get the entropy, let's say I wanted the entropy at 298 Kelvin. If I wanted the entropy of water at 298 Kelvin here, this would be liquid water, what I would do is I'd sum up the area under the curve up to 298. And then I know that the entropy at 0 is 0, something like that. So this is, if I wanted the entropy of the gas would be much greater because I'd be summing up more area under the curve. Basically, you don't need to know the details of this. But basically what we're going to do is we're going to be able to determine entropies experimentally. And so this is kind of the theoretical determination of entropy. This is kind of the experimental determination of entropy. Basically taking heat capacity measurements to very low. So our book doesn't really have, let's take a look. So it would be something like this, you know. I guess this heat capacity this is over T, should go down to 0. So my curve doesn't quite match that. Here. And then when we look at entropy, this is what it looks like because we're just summing up the energies. This is a solid to solid phase transition, but this is typically what we look at. Solid, and then there's a big jump to a liquid, and then another big jump to a gas. And so gases are going to have higher entropies than liquids, which are going to have higher entropies than solids. And so this is what we're going to do, is we're just going to look at the data. So let's look at the data here for entropies, absolute entropies. And that data is going to be Appendix D. So we use this data table a lot. So we aren't going to do any calculations, like I said, with it, but here, you know, for calculating delta H's of reactions, using delta H of formations are the easiest, you know, take products minus reactants. So column 1's very useful. Also column 3 here. Column 3 is going to be very useful because for calculating delta S's, we're just going to calculate the entropy, the absolute entropy of the products minus the absolute entropy of the reactant. So it's a very similar calculation to delta H over here, except we're using absolute entropy. Now, let's take a look at some of the entropies here. And so, for example, aluminum, we call this a pretty low entropy because, it's a solid. Aluminum is a solid at room temperature. It forms a crystalline solid, a metal crystal. It forms in a body-centered cubic structure. And so it's pretty low entropy here. We're not going to pay attention to heat capacities over here. Like we're not really going to do anything with heat capacities here. But, and so that's pretty low. Whereas, let's see, do we have molten aluminum? We don't have molten. Let's look at some other solids. Here's another solid, aluminum chloride. It has a little higher entropy, aluminum chloride, 110. But look at this one, dialuminum hexachloride gas. Now this forms a molecule. It has much higher entropy, 490. Now, what are the units for this? This would be joules per mole Kelvin. So this is joules. And so solids have lower entropy, gases have higher entropy. So let's kind of estimate, okay, except this solid. This solid, when we look at this one, this solid has kind of a high entropy, unusually high entropy, aluminum sulfate. It's probably because the sulfates aren't locked. It's probably because the sulfates might be able to rotate in the crystal structure. Sometimes that happens and increases entropy. Aluminum oxide, though, if you look at that solid, that's really well ordered. Aluminum oxide, alumina, 50.92. And so when we look at this, let's compare. Okay, barium solid, 62.8. Barium carbonate, 112. Barium chloride, 123. Barium fluoride, 96. Barium oxide, 70.42. Now this solid has a fairly high entropy. This is barium hydroxide, octahydrate. This is probably because the water molecules might be able to rotate in the lattice or other things that might increase the entropy, but this is a little high. Barium sulfate, 132, compared to aluminum sulfate, it's quite a bit lower. Beryllium is really pretty well ordered, 9.5.
The aluminum in the aqueous solution kind of negative.
Yeah, we need to talk about, I'll talk about that in just a moment. But when we look at this, what's a typical entropy of a solid, roughly?
15, 20.
Yeah, maybe from around 0 to, let's see what the lowest. Diamond, look at the entropy of diamond. 2.38. Diamond is around the lowest. Pretty well ordered. But typical solids are around 0 to about what? 50, 100, maybe 100. Let's do 100 because that will capture more of it. And then you have some outlier solids that have higher entropies due to one reason or another. And so typical solids are around 0 to 100. Let me tell you about liquids. If we look at liquids, like carbon tetrachloride here, carbon tetrachloride is 216. And then there aren't that many liquids here. C3O2 liquid, 181. CS2 liquid, 151. So based on this data so far, what would you say liquids are roughly? So solids are about 0 to 100, and liquids would be about what?
101 to 200.
Yeah, 100 to a 200. And then gases should be, let's take a look at some gases here. Cl2O, 266, 256, 281, 223, 165. So gases are around what? Over 200. And so this is typically what we do. If we're just going to guesstimate the entropy, then we'd say solids around 0 to 100, liquids are around 100 to 200, and gases are over 200, like 200 to 300. And then there's going to be outliers both ways. Some liquids are especially well ordered, some solids are especially well ordered as well. Now, what's going on here with aluminum 3+? Because if I recall, the third law of thermodynamics states that the entropy of a perfect crystal is 0. Why is it 0? Because there's only one way to arrange things. And when we plug that in here, If there's only one way, then the lowest entropy should be 0. And the third law is important because of this. Third law allows us here to put the initial entropy as 0 and the final entropy is whatever we calculate there. But this appears to be even better ordered than a perfect crystal at 0 Kelvin. Is that possible to have less than one way of arranging things? No, so something is very wrong here. So maybe you think that's a typo? Maybe that's a typo. Sometimes typos happen in books. Do you see any other negatives there? But when we get here, look at it. Negative. Cadmium 2 plus aqueous. Negative. Calcium 2 plus. Yeah, they're ions. And not only that, what kind of ions are they? Because if we let's look at an anion. Well, anion here. Let's look at a simple anion here. If we look at a simple anion, take a look. This one's 56.5 chloride. As the anion gets a little bit more complex, like carbonate, it's minus here. But what's going on with the ions is this. The same thing happens for delta H of formation. And do you guys recall what the formation reaction is? Formation is formation of 1 mole of species from the elements in their most stable state. And so if we look, for example, the delta H formation of chloride is minus 167.2. Okay, so we're forming chloride from chlorine. And we're going to get minus 167.2 kilojoules worth of energy. But let's take a look at delta H formation of H plus. If we look at delta H of formation of H plus and compare that to delta H of formation of H2, delta H of formation of H2 makes total sense. Because we're going from H2 gas to H2 gas, there should be no change in energy. But this one does not make sense. Delta H of formation of H plus doesn't make sense because we're going from H2 gas to 2H plus aqueous. Does that cost really 0 energy? No. And so the exact same thing happened here. Do you guys recall what happened here? And so think about that, because that's wrong. This is wrong. In order to take hydrogen and make it H plus, we have to break a bond, and then we have to ionize it. Breaking a bond costs energy, ionizing it costs energy. And then we're going to get some energy back by forming hydrated H plus. And so do we get the exact same energy back? It turns out, no, we don't get the exact same energy back. There is actually an energy change here. And so this is one other thing that sticks out. This is a problem. And so how was the problem resolved? So we'll talk about that next time, or think about it, Let's see.
And is that H? I'm guessing this is all half reaction, right? You can't just have H reacted without you.
Exactly. That was the problem. So if you go back to chapter 7, whatever it is, it talks about this. There's a paragraph in there that talks about you can't form a cation without an anion. And so we'll look at it again, just as a review.
For tomorrow, is there a lab?
No. Tomorrow is the computer lab, so we're going to work up more data, the kinetics data, and then work on the reports.